A while ago, I had the opportunity to sit in on an appointment between a physician and a patient. And after the patient left, I recall the physician indicating in his notes that the patient responded with a first order response. And I'm thinking to myself, what does a first order response mean? In this video, we're going to take a look at basic concepts in chemical kinetics and the concept of the response order of a reaction based on concentrations. In other words, how fast will a reaction go if you alter the concentration of a reactant? And we're going to use a hypothetical medical dosage example. And I want you to imagine that we have a patient who has a headache and takes 1 aspirin. And the response time is 1 hour, and that's our baseline. Well, what would happen if we double the dosage? Well, if you double the dosage, you would expect that the patient responds to, the reaction goes 2 times faster. And that is an example of a first order response. A first order response is an expected response. How many times faster? 2 to the first, or in other words, 2 times faster. So if it's 2 times faster, the response time would be 1/2 hour compared to the original 1 hour. Now, if we were to graph the concentration of the medication over time, what would our graph look like? Well, at time 0, we would have 100%. And let's say that there's a hypothetical half-life of 1 hour. After 1 hour, the medication, 50% of it would remain. And then after another 1 hour, half of that half, 25%. And then after another 1 hour, half of that half, or 12.5%. And then after another hour, 6.25%. And our graph would look like this. And the key here is that we have a consistent half-life. The half-life is the same at all times. That is an example of a first order response. However, there are times where you introduce medication to a patient and the reaction occurs 4 times faster. That would be an example of a second order response. How many times faster? 2 to the second times faster, or in other words, in this case, 4 times faster. And if it's 4 times faster, then that means that the effect of the medication, instead of 1 hour, is going to be 1/4 of an hour. So 2 to the second power, second order. Our first order, 2 to the first order, 2 times faster. Now, the concept in a second order reaction is that the half-life changes over time. In fact, it gets twice as long as the previous half-life subsequently. So for example, let's say that we have 100% in the system, and let's say that after the first hour, 50% will remain. But then if the first half-life was 1 hour, the subsequent half-life, the next half-life would be 2 hours. So that would mean that we're at 3 hours for 25%. And then the next half-life would be 4 hours additionally there. So that to get to 12.5%. And then the next half-life would be 8 hours. And that would get to 6.25%. And our graph would look a little bit different in the first order. Now, there are cases where you introduce extra medication or increase the concentration of a reaction, and there is no effect on the reaction rate. So that would be an example of a zero order response. No effect. No effect. How many times faster? This occurs 2 to the 0 times faster, or in other words, any number raised to the 0 power is 1, or in other words, 1 time faster, which basically means that's the same speed or the same rate. So 2 to the 0, again, the order is the exponent here, 2 to the 0, 2 to the first, 2 to the second. And what would that look like? That means that you introduce a medication and the medication just degrades and there is no half-life here. So there is no half-life. We have just a straight line consistent decay. Now, We want to oftentimes replot data in a linear format. That way we can do analyses and see what would happen if a patient, for example, is taking multiple medications. What is the ideal dosage to give the patient if they're taking maybe medication for gout to medication for arthritis, another blood thinner. And we want to replot these graphs in a linear manner in order to find intersection points and further analyses. So this is where the mathematicians come in. If we have a first order, which is the concentration versus time, a consistent half-life, this is not a linear graph. But if we were to replot this as the natural log of the concentration versus time, then these points here would fall into a line and give us a linear graph. And the slope of that graph would be, in this case, it's a negative slope, downhill slope, negative k, and lowercase k, that is our rate constant, specific for the reaction. Now, in math class, back in the day, you probably learned or may be familiar with this, y equals mx plus b. If we want to write the equation for a line, y would be the y-axis, or in other words, the natural log of the concentration of the aspirin. M is the slope, so that's going to be negative k. X is the x-axis, which in this case is time. And then b is the y-intercept, which would be the natural log of the concentration, the initial concentration. And this would be what they call the integrated rate law equation for a first order reaction. How about a second order reaction? In the case of a second order reaction, this is where the mathematicians come in. We're going to replot this as the reciprocal of the concentration versus time. And when you do that, these data points here would fall in a line with a positive slope, and the slope would be indicative of the rate constant for that reaction. And once again, y equals mx plus b. That's a generalized formula for the equation of a line. Y is the y-intercept, 1 over the concentration of A. M is the slope, which is k. X is the x-axis, which is time. And the B is the y-intercept, which is the initial concentration of the reactant. And for a zero order graph, this is already a line. Y equals mx plus b. Y is the concentration of the reactant. M is the slope. This is a negative slope, negative k. Rate constant. X is the time, and then the B is the y-intercept, the original concentration of the reactant. So what we have on the board over here is a lot of information here, going over the concepts of first order, second order, and zero order, and then extending to the graphs and what would those graphs look like and what would the integrated rate law equations look like. And we're going to use those equations in subsequent assignments.